Hello, I'm going to do another quick example derivation in URSA. This time I'm going to derive the impulse for the Hohmann transfer orbit, which is a transfer for switching between two circular orbits, and it would be useful for something like sending a space vehicle from the Earth to Mars. So I'm going to derive the impulse. I have this Wikipedia page open for reference. I'm going to basically start with this energy equation and derive this delta V. So we're going to start with that, and we're going to derive this intermediate equation along the way. So the first thing that I need to do is enter the equation that I want to start with, and that is done with the expression .set command. So I'm just going to type this in, mv squared over 2 minus, and by the way, this is e equals this stuff equals this other thing. I'm not using the e, I'm just going to use this right-hand part. And this equation could be derived from something prior to it. I'm not doing that here. You've got to start somewhere, and I'm starting here. So, minus g times big M times little m over r equals negative g times big M times little m over 2a. So we're starting here. And we want to derive this equation. So we're going to need to isolate the v squared on the left-hand side. A good first thing to do is add this middle term to both sides. And there's a command called equality.add that adds a term to both sides. So I'm just going to add g times big M times little m over r. That gets added to both sides. And now I'm going to invoke the simplify rule to cancel these terms. Simplify and cancel terms. And I'm not going to go into details about how exactly simplify is implemented, but it basically tries to simplify expressions. Now we've got just mv squared over 2 on the left-hand side, and to continue isolating the v squared, we can multiply by 2 over m. So there's a rule equality.multiply, which multiplies both sides of an equality by a term. So I'm going to multiply by 2 over m, and then simplify again. And now we've got v squared equals this sum times 2 over m. Now, the simplify rule does not distribute things out right now. Maybe it should, but you might have a big summation where you maybe don't want to distribute, so I'm not sure. It doesn't right now. But I will distribute this manually and then simplify again. And now it looks pretty simple. And we'd like to get the form of the equation to what's over on this Wikipedia page. So I'm going to start by factoring out big G times big M. Factor big G times big M. That's a command that factors something out of an equation. And that is what mu is defined as. Mu equals gm. So I'm going to go in here and just use expression.set again and change this to mu. Now, there are more rigorous ways that you could define variables, but for our purposes it will suffice to just use expression.set and call that mu. So now we have this thing that mu is multiplied by, and we can just use the swap command to reorder the terms in here. Swap the terms of the sum and then swap the terms of this fraction. You'll notice here this is, in the expression tree, it says it's the product of the reciprocal of r with 2, which is why the 1 over r appears on the left-hand side. So when we swap that, we get this nice fraction. So now we've got this derived, and we'd like to get this impulse. Now this delta v is the difference between the velocities under two different sets of conditions. This equation, v squared equals mu times 2 over r minus 1 over a, this is referring to orbits. And v is the velocity at a certain point in an orbit. R is the radius that you're at in the orbit, and a is the semi-major axis. So this is true for any orbit at any point. And we're going to derive this delta v for basically when we're switching from orbit 1 to orbit 2. And that happens at this point down here where they coincide. So really, to get this delta v, we're going to want to solve for v twice and subtract them. So we're going to want 2 copies of this equation. There's a command called sequence.next, which basically clones an equation and makes 2 copies of it. So running that, we've now got 2 copies of the equation. Now I'm going to start substituting variables. We've got two velocities, and I'm going to call them v1 and v2. And I'm going to start substituting things using a rule called bind. Now, this rule, I would like to give this a better name, but basically it replaces a variable with another variable. So in this top equation, I'm going to replace v with v1, and then I'm going to replace r with r1, because the state of the system at this first orbit is the radius is just r1. And then in that first blue orbit, it's circular, and the semi-major axis A is also 1. So I'm going to say bind A to R1. Semi-major axis is also R1, I think I meant to say. And now we're done substituting variables in the first equation. So for the second equation, I'm going to call V V2. The radius, R, is still R1, because the point that we're at is this point where they coincide at radius r1. And then the semi-major axis, the state of the object in this second orbit, is this orange ellipse orbit. And the semi-major axis is now, it happens to be r1 plus r2 over 2. It happens to be the average of the two radii, the blue one and the red one. So I'm going to replace A with our new semi-major axis, which is the average, r1 plus r2 over 2. And now, there's a couple things that we'd like to clean up here, I think. One is that we had an a in the denominator, and I replaced it with a fraction, so now it's a nested fraction. And the simplify rule will clean that up. Another thing to notice is that in this top equation, it's 2 over r1 minus 1 over r1. Which we can simplify a little bit. The simplify rule is not smart enough to take care of this yet, but we can just clean it up. We can factor out an r1. Factor out a r underscore 1. And then we've got 1 over r1 times 2 minus 1. Basically, these rules, if the simplify rule is made smarter, it will basically be doing what I'm doing manually. It will just detect that this stuff is a good idea and do it. That's sort of how this works. It pattern matches on the equation and decides what to do. So now we've got 2 minus 1, and there is a command called add numbers, where you can just tell Ursa to add some numbers. So 2 minus 1 is 1. We can simplify this to get rid of the 1. And now this is a simpler equation. Now, we are almost ready to subtract these, but we want to take v2 minus v1, and we've got v2 squared and we've got v1 squared, so we want to take the square root of both sides. Now, the way that we do that is there's a rule or a command called cong. It's equality.cong. And cong stands for congruence, and it implements that equality is a congruence relation. So you can apply a function to both sides of an equality, and it remains true. So I can say cong square root, and this will take the square root of both sides of the equality. And you can use any function with cong, like we can take sine of the both sides of the equality. We get sine of, but we don't really want to use the sine function here. We want to use square root. Cong square root. So now we've got the square root of both sides. And we want to take v2 minus v1, but we've got the square root of v2 squared and the square root of v1 squared. So we want to eliminate the square root. There is a rule called square root elim that eliminates square roots. And if I run that now, you'll see what happens. It says, could not satisfy constraint positive v1. Really what this rule should do right now is replace this with plus or minus v1. That's not implemented yet. The only thing that square root elim does right now is replace the square root of a positive number squared with just that positive number. And it says it could not satisfy positive v1. So we need to basically tell Ursa that v1 is positive, and we do that by saying assume positive v1. And I copied that to my clipboard because I also want to assume v2 is positive. And that shows up in this tree here under assumptions, user, positive. We now have two assumptions, positive v1 and positive v2. And basically the square root just queries these assumptions and checks that the thing is positive. And assumptions can be inferred from other assumptions, but we're not going to go there here. You can, in principle, do things like, if two things are positive, then their sum is positive, and Ursa will just figure that out. But we're not going to go into exactly how that works here. We just asserted that these two things are positive, and now we can use the square root of lim rule. So now we're just about ready to subtract these, but we want to take v2 minus v1, so we're going to use the congruence rule again with neg, which is additive inverse. So that just takes the negative of both sides, and then maybe swap the order of these equations in the sequence, and then we can recombine these equations with a command called sequence.add. This adds up all of the left-hand sides and all of the right-hand sides of a sequence of equations. So I run this, and now we've got that v2 minus v1 equals this root minus this root. And this is laid out like this. The terms in these sums are one on top of another. And that would be what you want if you had really big terms or a lot of terms, and otherwise they'd go off the edges of the screen. But these terms are pretty small, and there aren't very many of them, so we can just change the layout back. We're going to want to do that. There are rules under layout. There's two. There's layout.default and layout.split. Default is just writing things from left to right, side by side, and split is split onto multiple lines like it is now. So we can just change that with this layout command. So now we've got the delta v on the left-hand side. That's v2 minus v1, which is nice. That's what we want. And then we want to work with this right-hand side and simplify it a little bit. The first thing to notice, since I would like to derive the form of the equation here in this Wikipedia page, the first thing that I notice about this is it's got this square root of mu over r1 factored out, so we'd like to factor that out of our equation. Now the nice thing is this right-hand side, this is square root of mu over r1, so that's nice. But the left-hand side, there's nothing to factor out. We have a mu, but we don't have a reciprocal of r1. So we need to add that in order to factor it out. Now, in principle, you could write a factor rule that just multiplies by r1 over r1 in order to factor out a 1 over r1. That's not what the factor rule does right now, but it could be a rule. But anyway, we're going to add that. There's a command called inv_intro that adds a term and its group inverse. So we've got this times operation that we're inside of. So if we say inv_intro r1, it'll add r1 and its group inverse, which is 1 over r1. So this just multiplies this by r1 over r1. Now we've got an r1 on the bottom that we can factor out. So we can go back out here and say factor out a square root of mu over r1. And this just factors that out. And I'm not going to go into detail here about how the factor rule works either, but it can factor square roots out of square roots. Now we're almost there. The next thing that we are going to want to do is simplify the innards of this square root a little bit. It will be useful to distribute this and then simplify, just so that it looks a little nicer. And then we've got 2 minus r1 over r1 plus r2 times 2. And we'd like to bring this over a common denominator. There's no command yet for combining fractions and creating common denominators, but we can do that kind of manually. We can take this 2 number. This is just the number 2, but there is a command called times_intro that just wraps something in a unary multiplication. So this just changes 2 to times 2, with times with one argument. And then we can use inv intro to introduce R1 plus R2 over R1 plus R2. And then this, again, there's no rule to bring things over common denominators yet, and that would be useful, but we can cope anyway by distributing this out. So we're going to distribute the top over this addition at the top, the 2 over the addition at the top, and we get this result. And then we can start simplifying. And now that just canceled terms, and we've got R2 over R1 plus R2 times 2. And it would be nice to match the form of the equation to what's here on the Wikipedia page. So we can sort of reorder terms. We can use the swap rule, and the swap rule actually takes these 2 arguments that are optional arguments, and they tell you which terms to swap. So if I put recip of k in here, it will swap the reciprocal with something. So then I can put in 2, and it will swap the reciprocal term with the 2 term, just change the order, and then I can run swap again, and by default, if you don't give it anything, it swaps the first 2 terms. So now we've got 2 times R2 over R1 plus R2, which does match what's on the Wikipedia page. So that's delta V1. Delta V2 I'm not going to derive, but that's similar. So anyway, there you go. There's the delta V for the Hohmann transfer orbit. See you next time.